All right, so welcome everyone to Lab 9. So we're pleased to have Dr. Mohammed Tahir with us. He's going to be our guest lecturer. He's actually one of the co-instructors as well, so he's working behind the scenes in developing those labs, and he's going to be involved with some of the projects as well. So I can say quite a few things about Tahir. I'm not going to spend too much time here. I mean, I'll let him speak. Right. So Tahir has a PhD from Politecnico Torino in Italy, and he has been with us for several years now. He works in the general area of signal processing. He works, I mean, one of his, I mean, the key point here is that he works a lot with undergraduate students for his research. So he's a proponent for undergraduate research. Many of our undergraduate students have gone on to prestigious schools, grad schools in the US because of his efforts. So today he's going to talk about one of those efforts. So this is, I think, the lab is about soil moisture sensing using radio signals. This started out as a senior year project a few years ago, and we're still continuing that research, and is related to the nursery visits as well. So when we went to the nursery, you saw some soil moisture sensors. So we're now going to look at a different way of a novel way of how we can measure the soil moisture. So over to you, Time.
Okay, thank you, Mohammed. So, Assalamu alaikum, everyone. Hope I am audible, Mohammed. Okay.
Yeah.
So welcome to this lab session. So it is about soil moisture sensing using radio signals. So as we will proceed, I will highlight what do we mean by radio signals that I'm sure some of you already know, and how we can use them for sensing the soil moisture or water content of a given soil sample. So before that, just an introduction about me. So Mohammed told something. So here it is a formal slide about my research group. So as you can see, we are 3 faculty members working in research group named as Smart Data Systems and Applications Research Group. So our expertise mostly lie in communication technologies, signal processing, and machine learning for applications ranging from smart health to urban development, industry, modernizing and automating the industry of Pakistan, and then smart sensing. So today we will be focusing, we will be seeing an application of smart sensing. So it is also known in computer science community as mobile computing. So these two are interchangeable names. So you can visit our website here for more details about our projects and also about the work that we are currently doing. So let's go back to our lab. So here you can see what I have compiled here. What I will be doing, I will be motivating why soil moisture sensing is an important topic, and why should we looking at not just only from agriculture point of view, but also from a broader perspective. So I digged up a little bit of information. So you can see here, so this little guy here, which is fungi called Tortubus, so which is the, I think, oldest known land fossil discovered around 440 million years ago. So plants and fungi were the first living organism that colonized our land. So as soon as they colonized our land, they had some advantages. As an example, there was no competition, so they had an ample opportunity to grow. CO2 present in the atmosphere was in abundant quantity, and today we know that CO2 is, for example, very important for photosynthesis. But at the same time, they also had some challenges. And you can see here I have listed 4 of them. So, for example, intense sunlight, risk of desiccation, and how to extract nutrients from the soil while surviving in the temperature extremes. So all of these challenges that the plants and fungi faced were related to only one quantity, which was how to extract water from the colonizing land. So what happens? Why water is so necessary? So it is necessary. Today we know that using photosynthesis, plants convert the light energy into chemical energy, and that chemical energy is essential for their working and for their, for example, reproduction, gas exchange, nutrient absorption and transport, and so many other metabolic functions. So what happens if we give too much water to a plant? So that is the motivation. We are starting from too much water. We already know what happens if we don't give water to a plant. That will be in the subsequent slides. So if we give too much water to a plant, there are two important phenomena. So for example, here you can see the leaves of the plants have turned yellow. So this is called rotting of soils. So they are not able to, the plants are not able to extract the nutrients from the soil properly. And then there is this leaching phenomena. For example, when there is excessive rains in an area, all the soil gets muddy and the plants are not able to extract the nutrients from the soil. So overwatering is as bad as underwatering. So what about underwatering? So wilting is very common phenomena where uh, the roots of the plant, they are not able to extract the nutrients. So as a result, the plant is something like that, as you can see here. So what happens? How do we actually irrigate our plants, or the practices that are used in agriculture? One common thing is predetermined schedule. So we already know that, okay, so we are going to water our plants daily, or we visually evaluate the water status of the soil, and then we decide that, okay, so we have to provide water or not. So both of these things, they may lead to underwatering or overwatering because it is a subjective assessment that we are doing. The solution that you have already seen in one of the field visits is sensor controlled irrigation. So what do we do in sensor controlled irrigation? So we have a system deployed here in the field, which is irrigation system. So these are valves controlled by a very intelligent controller, but these controllers are operated by, for example, this person who has a mobile application. The decision is made on the basis of these sensors. So the most important sensor you can see here is soil moisture sensor. So this sensor is going to send some readings over to, for example, computer or some mobile, where you will be making some intelligent decisions based on, I don't know, whatever the available data that you have. And then using this smart application, you can control how much, number one, whether the plant should be irrigated, and what should be the frequency, what should be the amount of water that is released by these valves. So you have also seen these types of watering system or irrigation system deployed in lumps, but there is a difference that is manually controlled. The people who are responsible for this system, they have a valve, they simply rotate it, the water just flows out, and then they simply turn it off after some time. So we are not talking about that system that is manually controlled. This is automatically controlled using a mobile app. Okay. So this leads us to motivating why soil moisture. So I started with agriculture application because we are more familiar with that thing. So how about soil moisture sensing in general? So on this slide, what I have done, I have tried to extract some of the applications apart from the agriculture where people use soil moisture. So as you can see, for numerical weather prediction or flood risk modeling. So if there are heavy rains, as you have seen in last 2 or 3 days all around the Pakistan. So what is the flood risk of a certain region? So that is directly related to the soil moisture content of that region. So here you can see another important thing. I will not be going in each and every one of these applications. There are actually a lot more. So for the understanding ocean land feedbacks, so how the water is exchanged between land and oceans, that is actually a very good topic for hydrology and land surface system research people. So in order to understand those feedbacks, that how the water is exchanged between ocean and lands, soil moisture modeling is very important. So as you can see, all of these, they are related, all of these application and even the agriculture, they are related to what? They're related to our earth, our climate. So keeping these things in mind, there is actually a United Nations run agency called Global Climate Observing System, GCOS. If you already know, then well and good. If you don't know, please go and visit their website. So they have actually recognized 54 variables. They call them essential climate variables, ECVs. So these 54 variables are either physical, chemical, or a biological group of variables which we can sense with very good accuracy. And these variables contribute to characterize Earth's climate. As today we know that climate change is a real thing which is happening right now. So these 54 variables, according to GCOS and United Nations, must be observed and monitored in order to characterize the climate of our Earth. So soil moisture has been included in these essential variable list. The other 53 variables, they are from land, ocean, and atmosphere of our Earth. So just please visit this website, GCOS. This is a body of United Nations, so which is responsible for giving the feedback about to the scientific community about how what steps they should take to control, for example, global warming or Earth's climate. Okay, so this is it about introduction. So now how about soil moisture sensing? So soil moisture sensing means we should know the water content of a given soil sample. So when we talk about soil moisture sensing, there are two clear distinctions between these quantities. So first is, for example, here this is this green plant. So starting from the land to the depth of 5 centimeter, we call it surface soil moisture, which is usually related, and we only observe it if we are doing visual inspection of the soil. But then there is something which is quite in depth. We call it root zone soil moisture. So it is much more valuable, for example, for precision agriculture. So just to keep in mind, in this lab, we will be focusing only on surface soil moisture due to the reasons, as I will tell you, that radio signals cannot propagate enough inside the soil sample. But there are models which exist to relate this surface soil moisture to root zone moisture. And these are very accurate mathematical models, which means if you know the surface soil moisture and some characteristics of the soil sample, then you can get the root zone moisture using those mathematical models. Nevertheless, this surface soil moisture in itself is an important variable, which is, for example, here I have written, which is related to so many parameters. So it is something that it's something that we must observe. Okay. So proceeding with soil moisture sensing, there are actually three ways in which we can quantify soil moisture contents of a soil sample. What are these three ways? So one is what we call gravimetric water content of a soil. So gravimetric water content means measure the weights of water in the soil, measure the weight of total soil sample, water plus soil, and then compute this percentage. That is called gravimetric water content. Then there is volumetric water content. Instead of mass or weight, they operate on volume. So volume of water divided by volume of soil sample, and then computed in percentage. And then third is soil metric tension or soil water potential. So there is a device, for example, here you can see this is called tensiometer, which is a soil moisture sensor. So what happens when you have to measure soil moisture, you have to insert this sensor into the soil, and then there is this water in the tube. So if the plant or the soil is really thirsty, it is going to suck this water out of this tube, and then based on the amount of water that is being sucked by the roots of the plant or the soil sample, you can calibrate how much soil moisture content is there in the soil moisture. So these three are the only methods which are used for soil moisture sensing, not methods. These three are the only ways to quantify how we can measure the soil moisture. So of course, we will be focusing here on volumetric water content. Why? Because it is most widely used, number one. Number two, there are very cheap sensors, as you have already seen in your field visit. I will also be telling you something about these sensors, which are based on very simple principle of measuring the capacitance of the soil sample. So these sensors actually provide you volumetric water content. Okay. So in order to measure volumetric water content, we have 5 different techniques or methods. So first one is very classical one, we call it time domain reflectometry. So the device is something like this. You have 3 pins. Using 3 pins, what do? You put a voltage pulse. So I hope every one of us knows what is a voltage signal. So you put a voltage pulse which propagates into the soil moisture and then comes back. So based on the velocity of propagation, you compute another property of the soil, which we call dielectric permittivity, which is directly related to water content. Okay, so in this way, we are able to measure what is the amount of soil moisture present in our soil sample. Then second method is, as I have already told you, the most widely used capacitance devices. So you also need to put these devices into the soil sample, as you can see here in this figure. So they determine the capacitance of the probe, this probe which is inserted into in or near the soil. So this capacitance is actually function of the water content around it. So based on the capacitance sensed, we can calibrate how much is the water content of the soil sample. So they're very low cost, very cheap, and very widely used, and are available in many different configurations and shapes. Yes, these are the sensors that you guys have already seen in nursery, LUMS nursery during your field visits. These are very cheap sensors. Okay, the problem with the previous one, time domain reflectometry, and this capacitance devices is you need to put them inside the soil. So we call them invasive sensors. You need a person in charge who is going to put these sensors into the soil so that you can get the reading or the signal out of these sensors. But the issue is, if we have to sense the soil moisture of for example, of a field having hundreds of hectares, and how can we do that? So the method is non-invasive sensing. So for non-invasive sensing, first principle is what we call ground penetrating radar. So ground penetrating radar is a cart, something like this, as you see here. So the farmer or the person in charge is going to drive it over the field and simply drive it. There is absolutely no contact between anything present in this card and the underlying soil moisture or the land. You simply drive it, it sends electromagnetic pulses. Okay, shortly I will tell you what are electromagnetic pulses. Actually, electromagnetic pulses are the radio signals. So it emits radio signals. Those radio signals go strike the land or the soil, and then they are reflected back. When they're reflected back, there is a very sophisticated algorithm which simply processes it, and then you can get a map. For example, you see here this map. So for example, this is 0 to 5 centimeter or 0 to 10 centimeter. It gives you volumetric moisture in the form of this map. It's very effective method, very widely used and non-invasive. But the problem is this device here, it is very, very expensive, and you need very sophistication in getting this map. But it is for sure non-invasive method. The fourth and fifth method, they are actually based on what we call remote sensing. So what is remote sensing? So remote sensing, you have an airborne or spaceborne thing. For example, spaceborne means you have satellite, and airborne means, for example, you have a drone. So you deploy something on this drone or on this satellite, which transmits a wave. That wave is reflected back, and based on the properties of the transmitted and reflected wave, again, this wave is radio signal, you are able to sense, so what is the soil moisture of, for example, surface from where this wave has reflected back. So this is non-invasive method, but the problem is it has very low spatial resolutions. For example, you can get the soil moisture of 10 kilometers of a region, especially with satellites. So this is called active remote sensing because this platform, whether spaceborne or airborne, first transmits a signal and then that signal is received back. So that is why it is called active. In contrast to this, there is another approach is called passive remote sensing. In this remote sensing, the airborne or spaceborne device does not emit anything to the Earth. Rather, it only observes the radiation or the radiance which is reflected from the surface. So now this is much more sophisticated as compared to the previous one because you have to tune your devices to a particular band to observe this energy which is actually reflected from the Earth's surface. So the problem is again very low resolution and quite expensive setup. Now we got actually inspired from these. Okay, before we move to discuss our idea, let's compare them. So this red thing on your left, this is two methods which are based on invasive things, so time domain refractometry and capacitance devices. So what are their pros and cons? So they are very accurate, they are low cost, but they are cumbersome. You need special persons to deploy them, and they are invasive. So you have to put them on so many places in order to cover, for example, a complete field. On your right hand side, you have three methods which are easy to use, can provide you large coverage, non-invasive, but their resolution is very low. So non-invasive property is very appealing to us. So based on these things, we started with the idea. So let's use this principle of electromagnetic wave transmission into the soil and then reflection from the soil surface and then observing its properties. Why to put a special equipment, for example, like GPR or satellite or drone? Why not to use already available signals around us? For example, Wi-Fi signal, which is already available to us. So if we can do that, what will happen? So no extra cost is associated. We know that Wi-Fi is present everywhere, at least in indoors. Even now, Wi-Fi routers are available which have ranges of a few kilometers. It will also be non-invasive. But before we can do anything, we have to, for example, check what is the feasibility of this method, how much accuracy we can obtain, and what will be the amount of resolution. So these are the questions that we need to answer first. So as scientists, what do we need to do? We need to do experimentation. So we need to design an experiment in order to answer these questions. So before I go in details of how we have actually designed these experiments and how we have used Wi-Fi for soil moisture sensing, let's say something about what is Wi-Fi and what is this all electromagnetic thing that we have discussing, that we transmit it, then we receive it, and then we analyze its properties. But just from a very intuitive point of view without going into mathematics. Okay, so radio frequency signals or radio waves or electromagnetic waves are actually traveling electric and magnetic fields. So now all of us know what are electric fields and magnetic fields. But if somehow we make them travel into the space, they become electromagnetic waves. So how we do that? So that is where electrical engineering comes in. So this guy here, you see James Maxwell, he is known as the founder of electrical engineering. So he actually from theory predicted the existence of these fields, that okay, if you do something like this, your fields will start propagating into the space. So it was just only in theory, there was nothing practical. Until in 1887, this Heinrich Hertz, he actually confirmed using experimentation the theory developed by Maxwell, and it confirmed that yes, you can actually have these electromagnetic waves, and you can actually do something to make them travel into the space. Now, but he was not able to conceive the big picture. So he, after his experimentation, he also wrote something like this, that I do not think that the wireless waves I have discovered will have any practical application. And now after 130 years, we know that it has changed everything around us. You can see TV signal, there are electromagnetic waves, radio, electromagnetic waves. You can see your 4G, 5G, 2G, everything is electromagnetic waves. So, by the way, before we proceed, if you go and compile a list of 5 or 10 or 15 or 20 most valuable equations that changed the mathematics and revolutionized the world, the equations proposed by this guy will always be in the top of that list because they are so important. We call them Maxwell equations in electrical engineering. Okay, so as I told you, if we make electric and magnetic fields travel into the space, we get electromagnetic waves. But how do we do that? So you see here, something which is a rod labeled as antenna. Okay, so it is nothing but what we call it conductor. So it is simply a conductor. So inside this conductor, what we have to do, we have to control the motion of electrons. If we are able to control the motion of electrons very carefully, then what happens that around this conductor, an electromagnetic field is generated, and using some properties of this antenna design and the wave that we have applied at and the signal that we have applied at the input of this antenna, we can make this wave travel into the space. Okay, so after some time, this looks like this into the space. So it is a field. For example, you see on this green one is electric field and this blue one is magnetic field. Now this is in space, but what I do, what if I take its magnitude? So if I take the magnitude of electric field, I get something like this. We have already seen this signal in your first or second or third lab, I assume, which is a sinusoidal wave. And if I get the magnitude of magnetic field and plot both of these simultaneously, I get something like this. So electric field is aligned along, for example, y-axis, and magnetic field is aligned along x-axis. They are always perpendicular to each other, as you can see here. But the most important thing is at any point in time and space, if I take the magnitude of these two fields and then divide them, the ratio that we get is exactly equal to speed of light. Now, this is an astonishing result. No one knew before Maxwell that this is going to happen. This was hidden in the laws of nature. So, and this is true at all times and all locations in space. So what happened? So these are the words of Maxwell, who wrote down right after he discovered his Maxwell equations. So he said that the velocity means this ratio, is so nearly that of light that it seems we have strong reason to conclude that the light itself is an electromagnetic wave. And today we know that it is true. The light itself is an electromagnetic wave, and electromagnetic waves propagate at the speed of light. Apart from light and these radio signals that I have talked about, there are many other forms of electromagnetic radiations. And what are those forms? So this slide simply tells you that radio waves and our visible light, they both are electromagnetic waves, as you can see here. So apart from light and radio signals, there are so many other electromagnetic radiations. By name, we know some of them. For example, X-rays. So all of us almost know what are X-rays or gamma rays or ultraviolet or infrared. So radio waves, I'm sure you guys now know what is frequency and what is wavelength of a wave. So if if you look carefully, radio waves are the waves which occupy this smaller frequency region. So here frequency is small, but the wavelength is large, on the order of, you can see, of approximately in the order of this building. So as we start increasing frequency, we move towards visible region. So visible light, or the light that we see, is only this very tiny portion of this electromagnetic spectrum, only this thing. Below this, we have infrared and then radio waves. After this visible thing, we have ionizing waves, for example, X-rays or gamma rays, and they contain a lot of energy, and they are actually dangerous to humans or other organisms that come in contact with them. All right, so since we are talking about radio waves, so we will be focusing only on this part of the spectrum. And if we zoom this part of the spectrum, and let me show you what we have done on this part of the spectrum, we means humans. So this is some of the applications that people have used this part of the spectrum, which was radio spectrum, and developed a lot of applications. So starting from 3 kilohertz, you see there are these very big poles. We call them very low frequency. So the very low frequency communication. So they are, for example, used for navigation and guidance of these ships in the sea because they have very long range. So if we move towards the higher frequency region, we have, for example, you see here AM radio, then you have FM radio, then television, mobile phones, GPS, Wi-Fi, and then 4G. All of them, they are concentrated here in UHF band. So 5G and 6G, they are also envisioned somewhere here. And then as you move, you see you have satellite communication and then radio astronomy. So you see, these are the things that Hertz felt that the waves he has discovered will have no use. So I have just shown you a spectrum from 3 kilohertz to 300 gigahertz. So a lot of use. Actually, anything that you can imagine is here. For example, Wi-Fi. So Wi-Fi is just one technology that uses these radio signals or radio waves or electromagnetic waves to transmit data from transmitter to receiver and also backwards. So now let's move to what we were doing. So now we know that Wi-Fi is nothing but technology which uses electromagnetic waves to transmit the data. Now, how can I use Wi-Fi transmitter and receiver to do soil moisture sensing? So let's look at from the lens of electromagnetic wave. So you have Wi-Fi transmitter somewhere here, and then Wi-Fi receiver somewhere here. And between them, when you transmit data, so the data travels in the form of electromagnetic wave towards the receiver. Okay, so this is not a hypothetical thing. So this is somewhat very close to what your actual Wi-Fi signal looks like, but you do not need to worry. It is very low in energy, so you are not going to be hit by this arrow. Actually, there is no arrow here. Okay, so it just indicates the direction of propagation, this K thing. So what happens? These electromagnetic waves, including your Wi-Fi signal, they pass through bricks. Today we know, yes, they pass through glass, they pass through wood. But if you have a metallic object, most of the energy present in the electromagnetic wave is reflected back. Okay? So what we can do, we can put a material which is not wood or brick or glass or metal, some material. For example, here this material could be soil moisture, soil sample, जिसकी soil moisture हमने sense करनी है. So what will happen? Your Wi-Fi signal transmitted from the router will travel into the space. It is going to hit this material. Whenever it will hit this material, a lot of things happen. Physics tells us. So what does physics tell us? So you have, for example, depending on the type of the material, this signal or the wave can transmit all of it through this material. So we call it transmission. This phenomena, कि जो भी hit हुआ है सारे का सारा pass हो गया. Then there is another phenomena, we call it reflection. So reflection means कि wave आके hit किया, and then a portion of that wave is reflected in back towards the direction जिस direction से वो आई थी. So this is a reflection. Then you have refraction. So refraction means the wave has hit on the material it has bended, it has changed its direction, but it has passed through it. Then there are scattering, absorption, and diffraction, other mechanisms. The point is, these six mechanisms, they actually happen, and we can combine them into two things which are, for example, useful for our application. So you have an incident wave, something like this, which is going to hit this material. A portion of this incident wave will be transmitted from this material, and a portion of this incident wave will be reflected back. Okay? So this is the property of electromagnetic wave. This is the property of, for example, light, and so on. So what happens? Do we know how much portion of this incident waveform is reflected and how much portion of this incident waveform is transmitted? Yes, we do know, but it depends only on this material. So if we know the material physical properties, for example, we call it transmission coefficient of the material, then we can actually tell how much of the incident wave is being transmitted. And then there is another property, we call it material reflection coefficient. If we know that, we can tell that how much of the incident portion of the wave is reflected backwards. ठीक है? अब आप देख रहे हैं कि कैसे हम जो है वो वेव फॉर्म को बड़ा जनरल रखते हुए उसको मटेरियल की फिजिकल प्रॉपर्टी से रिलेट कर रहे हैं, और मटेरियल की फिजिकल प्रॉपर्टीज ही हमें बताएंगी कि हाउ वी कैन सेंस द मॉइस्चर प्रेजेंट इन दैट मटेरियल. सो नाउ वी हैव टू ऑप्शंस. ठीक है? सो इफ वी somehow can measure the power of the incident, transmitted, and reflected waveform. So I will tell you something. If you don't know about what do we mean by power of the signal, I will tell you. I will give you its expression. Why power? ये भी मैं आपको बताऊंगा. If we are somehow able to measure this power of these three waveforms, we can say a lot about the properties of this material present between incident and transmitted and reflected waves. ठीक है? So what our setup could look like. So one possibility is कि आप जो ट्रांसमीटर है वो यहाँ पे रखें, बीच में सॉइल मॉइस्चर जो आपका सैंपल है वो रखें, और उसके नीचे कहीं पे जाके आप वाईफाई रिसीवर रखें. तो होगा क्या? The wave will come, it will pass through the soil sample, it will be transmitted, some portion of this will be transmitted, for example here, and on receiver end you will compute the power of the transmitted signal. On transmitter end you will compute the power of the transmitted signal. You know these two powers. You can say what is the physical property, for example soil moisture content of this soil sample. But the issue is, in the setup you have to put the receiver below the soil sample. Okay, so this does not seem feasible. Rather, why not investigate the other setup? So in this way, what we do, we put the transmitter and receiver both above the soil sample, and instead of observing the transmitted waveform, what do we observe? We observe the reflected waveform. So now we will measure the transmitted power at transmitter, we will measure the reflected power at receiver, and then we can, using these two powers, P and PR, we can say something about the physical properties of this soil sample. So our experiment is based on this very much architecture जो कि यहाँ पे मैंने highlight की हुई है. All right. So as I have motivated that why we are going to put our transmitter and receiver in this fashion, now let's proceed. There will be only two or three mathematical equations, but they are necessary. We cannot avoid them, but let's try to understand them. So reflection coefficient, this symbol, if you don't know, is called capital gamma. So capital gamma here is equal to two things, numerator divided by denominator. So you have eta2 minus eta1. So this symbol is pronounced as eta. So what is eta? So eta1 is impedance of material 1. Material 1 means, for example, in our case, air. And eta2 is impedance of material 2, which material 2 in our case is soil sample. Okay? So if you know the impedance of material 1 and impedance of material 2, you can form this ratio. This ratio tells you reflection coefficient. If you know the reflection coefficient, you can actually tell how much portion of the incident wave is reflected back. So you need to simply multiply it. Okay, but it is very difficult to directly measure the impedance of soil sample. So we move further and we relate this impedance to other quantities. So these two quantities, which is termed as and pronounced as mu, and in the denominator, it is pronounced as epsilon. So eta is given by square root of mu over epsilon. So this is true for material 1. This is also true for material 2. So what is mu? Mu is called relative permeability of the material relative to free space. Okay, and this mu almost stays same from one material to other material unless the materials are really magnetic materials. And this epsilon here is called relative permittivity of the material relative to free space. Okay, that is why we have this R. Soon we will skip this R. Okay, so this quantity, relative permittivity of the material, varies a lot. As an example, in the table, please observe as we move from air to dry soil to pure water, the permittivity increases from 1, almost 1 to 3 to 80. Now, if I take dry soil and pure water and mix them, then I can expect that the relative permittivity hogi, that is going to be between 3 and 80, depending on what was the कि वो जो वॉल्यूम आपने सॉइल का मिक्स किया और जो वॉल्यूम आपने वाटर का मिक्स किया, कौन सा वॉल्यूम ज्यादा है. ठीक है, so depending on volumetric water content of the soil sample, you will get a permittivity value between 3 and 80. Right? So this is the thing that we will be using in our experiments, but indirectly, not directly. I will tell you how. So this is just the expression that we have seen on the previous slides. So now what we have to do? What will happen? As soil moisture will increase, this permittivity value will increase because dry soil has permittivity of 3 and pure water has permittivity of 80. As you will increase the water content of dry soil sample, the permittivity is going to increase. If permittivity increases, you can see from these two relationships, reflection coefficient increases. This gamma thing, this is called as reflection coefficient. If this increases, a greater portion of the incident waveform is reflected backward towards receiver and smaller portion is absorbed and transmitted across the sample. ठीक है, तो हमारा जो सिग्नल इधर आ रहा होगा रिसीवर के ऊपर, एज सॉइल मॉइस्चर विल इंक्रीज, जो सिग्नल इधर आ रहा होगा उसकी पावर इंक्रीज करना शुरू कर देगी. दैट इज द थिंग वी विल बी able to sense, और उससे हमें पता चलेगा कि what are the soil moisture content. But let's take this reflection coefficient thing here and let's take its so this reflection coefficient is really related to soil moisture as I have described it. Now let's take this reflection coefficient and take its logarithm. ठीक है, so all of us know कि हम जो है वो 20 log जब ले लेंगे तो जो हमारे पास quantity आएगी वो इन किस units में होगी? We call it dB units, decibel units. So this quantity here we define it or we name it as reflection or return loss, which is 20 log of absolute value of this gamma. Now this gamma is nothing but ratio between, as I have already told you, received power to transmitted power. अब ये received power और transmitted power we are able to measure it. कैसे? जो transmitted power है वो transmitter से हम खुद ही transmit कर रहे हैं सिग्नल. अच्छा, अभी आप ये सोच रहे होंगे कि जो transmit कर रहा होता है वाईफाई राउटर, उसमें तो हमें नहीं पता होता कि पावर क्या है. तो just for the sake of curiosity, हम जो आपके घरों में राउटर है वो नहीं यूज करेंगे, हम एक कस्टमाइज बिल्ड राउटर यूज करेंगे which allows us to measure the transmitted power. वो भी मैं आपको दिखाता हूँ थोड़ी देर में. Similarly here receiver actually हमें allow करता है कि जो आपका सिग्नल रिफ्लेक्ट बैक होके आ रहा है from the soil sample, you can actually sample it and then you can compute its PR, which is received power. So given a soil sample and its volumetric water content, we know this PT, we know this PR, we can form this ratio. We can form this ratio, we have our return loss. And that is, and we know that this return loss is then related to, for example, soil moisture content. But how to compute this power? So for example, if you get this signal, you can plot it in MATLAB, you will get something like this. So this is the first sample, this one is the last sample. So the power, whether at transmitter end or receiver end, you compute using this formula. So if this red signal is x of n, x-axis is n, y-axis is x of n, you simply take absolute value of every sample, square it, and then sum it. Whatever you get, you divide by total number of samples, which is n. So in MATLAB, you will do something like this. So if you have xn defined as, for example, as a sinusoidal wave, I'm sure you have used this function sine in MATLAB. So in order to compute the power of this x of n, we have implemented nothing but this formula. So you see, so x of n to have, jo yahan pe ye x of n nazar aa raha hai, this is this x of n. So first you take its absolute value, then square it, then sum all of them, and then you divide by 1 over capital N. So capital N is total number of samples, for example, 100, 1,000, or 2,000, whatever total number is. So using only this single line, we are able to measure the power of reflected signal. ठीक है जी, so let's move and design our experiment. क्योंकि अब हमें पता चल गया कि हमारे पास PR है, PT है, we have to simply measure them in MATLAB, and then that will give us this quantity reflection or return loss. Okay, so this is our setup. So what we did, you see here, this bucket contains dry soil. So we take the soil from the nursery. So we measure its volume using quite big cylinders. So then we put that in this bucket. Then we take water in those cylinders. We put that water in the soil and then we mix them uniformly. In this way, we already know what was the volume of the soil and what was the volume of the water. After preparing them, we know that this soil sample has this much of volumetric water content. So volumetric water content is actually known to us before experimentation. If that is known to us, what is unknown? We want to see if this volumetric water content of the soil is varied. अगर मैं इसको change करूं from one bucket to another bucket, we had actually 4 to 5 buckets. So how does this reflection or return loss behaves? How does it change? Is there any particular pattern which it is going to follow? And the result of the experiments, okay, before we go to the results, you see here, there are some other equipments. So you have these white boxes. So this white box is Wi-Fi transmitter that as I told you, but this is not the typical transmitter that you found in your houses. This is a transmitter which allows us to generate our own Wi-Fi like signal. It only takes that signal and transmits it using this green antenna. You see here it is an antenna. The other one is Wi-Fi receiver, which receives this signal and then gives us the sampled signal in MATLAB. In MATLAB, we can process it. Okay, so coming back to our original thing that we were doing, so we actually measure the pattern of this. We actually observe the pattern of this reflection or return loss as a function of volumetric water content. And here we plot what we have obtained. So you see, on y-axis, you have return loss or reflection loss, and on x-axis, you have volumetric water content, which we know. For example, this 0 corresponds to pure dry soil. ठीक है, तो हमने नर्सरी से मट्टी ली, उसको हमने काफी दिनों के लिए रख दिया. So when it was dried, we used that here. So it has 0 water content. So we used that here for experimentation. And we did many experimentation, and then we averaged the value of this reflection loss, which was somewhere here. फिर हमने क्या किया? We took another soil sample. ठीक है, we put volume, we put water in the soil sample so that the volumetric water content is 6%, around 6%. And then we used that for experimentation. We did multiple experiments. We averaged this quantity and we plot it here, and so on. Okay, so x-axis was known to us. We were interested in observing this y-axis, which was return loss. So now what does this show? This shows me that this is my model in the given settings for measuring soil moisture content of a given soil sample. Kaise? So in the given setting, someone comes with unknown volumetric water content, और वो आपको कहता है कि अच्छा मुझे बताएं इसमें soil moisture क्या है. So what will you do? You put that soil moisture content here. You will run your experiment. You will get a value of return loss. For example, you will get 20. So if you get 20, then that 20 you will simply extrapolate it over this curve. So when you will extrapolate it on through this curve, you will get this point. Then you simply have to look on the x-axis. So on x-axis, you have this value, which means around 0.049. Okay, so you will tell that guy that the given soil moisture, the given soil sample that you have has water content of around 5%. Okay, so in this way, we have obtained this model for measuring soil moisture content of any given soil sample. But how good is this model? Is it reliable? Is it repeatable? How much accurate it is? We don't know. Of course, we need a benchmark. Without any benchmark, our experimentation is of no use. We need to validate it. So in order to validate with a benchmark, we moved in a reverse direction. So let me show you how. So this is the same soil sample. What we did in experiment was we transmitted a signal, we received it, we measured return loss using this formula, and we plotted that curve जो कि मैंने आपको दिखा दी. Now theory tells me that in my case material 1 is air, material 2 is some soil sample with unknown epsilon. Now epsilon क्या है हमारे पास? Permittivity of this soil sample. Since it is pure air, we know its permittivity, which is 1.0006. इसको अगर मैं वो the previous हमने एक formula देखा था उसमें substitute कर दूं और इसको मैं rearrange करूं, I get epsilon in terms of that reflection coefficient. ठीक है, यहाँ से ये जो gamma आया है ना, it is not this one. This gamma is experimentally obtained. ये experiment से आ गया. अब ये वाला gamma मैं theory से लेके आऊंगा. कैसे? By relating this gamma to epsilon of this soil sample. अब ये जो क्वाड्रेटिक इक्वेशन है इसको मैं ओपन करूं दोनों साइडों के, तो इसको मैं रिवर्स करके लिख सकता हूं समथिंग लाइक दिस. सो गामा विल बी इन टर्म्स ऑफ एप्सिलॉन. सो ये जो गामा आया मेरे पास, दिस इज थ्योरेटिकल वन. सो आई कैन नाउ कंपेयर दिस थ्योरेटिकल गामा with what I have obtained from my experiments. In this way, I can validate how good are my experimental observations. But still we have an issue. This thing was related to volumetric water content. ठीक है, लेकिन यहाँ पे मैं soil की relative permittivity से relate कर रहा हूँ. There is no volumetric water content, so I need a one step before that, which allows me to relate this epsilon to volumetric water content. अगर मैं वो कर लूँ, then the loop is complete, right? तो अब मैं क्या करता हूँ, अब मैं चूंकि मेरे पास कोई information नहीं है, so I go and I search literature. Is there any formula or any model which relates this epsilon to volumetric water content theoretically? And we were lucky enough to find this equation, which is very well known in soil chemistry community. So this is called TOPS equation. So TOP is the name of the scientist who actually discovered this equation. So this equation, he developed it using empirical observations. So empirical means there is no theoretical foundation to it. Rather, you do measurements, a lot of measurements, thousands of measurements, and then you try to fit those measurements using some relationship. For example, this relationship here in our case. So since it is a benchmark used in soil chemistry, so we use this equation to relate the epsilon to theta v. Now our job is very simple. कैसे? देखिए मेरे पास जो है वो थीटा वी नोन था जब मैं एक्सपेरिमेंट कर रहा था, जैसे मैंने आपको बताया. सो थीटा वी वाज नोन टू मी. So theta v was known. I can use that theta v to put here in this equation to get this epsilon. ठीक है, so this is an equation, इसको हम solve कर सकते हैं. आप लोग अभी अपने lab task में use भी करेंगे. We have a function, built-in function जो कि आप use करेंगे, जिसमें आप epsilon जो है वो compute करेंगे given theta v. Using this epsilon, we can get gamma. Once we have this gamma, we can simply take its log. Now, this log will be compared with this quantity, 20 log of gamma will be compared with that gamma जो कि हमने experiment से लिया था. And these are the comparison results. So this blue one is the curve that we have already seen. Sorry, black one is the curve that we have already seen using experiments. And this blue one is the curve that we have obtained using Top's prediction, Top equation. It is good because the trend is same, but it is bad because there is a constant offset. So why is there some offset? So there could be multiple reasons. For example, आपके पास आप power compute कर रहे हैं ना transmitter end पे और receiver end पे experiment में for this black curve. So it may happen that there are some phenomena which you have neglected in computing that power. क्योंकि आपने बिल्कुल उसको मॉडल कर दिया कि आपने जितनी पावर ट्रांसमिट की वो या तो रिफ्लेक्ट हुई है या ट्रांसमिट हुई है. फॉर एग्जांपल देयर आर सम अदर फिनोमेना लाइक स्कैटरिंग और मल्टीपाथ जिसको आपने टेक इनटू अकाउंट नहीं किया तो उसकी वजह से कुछ पावर लॉस हो गया. ठीक है, बट द गुड थिंग इज इफ यू कीप द सेटिंग सेम देन दिस ऑफसेट इज कंसिस्टेंट. सो this gives us a way to remove this offset. Kaise? Just look at this one. This is dry sample. Na? So what I can do, I can calibrate my equipment or I can calibrate my settings for theta v equal to 0. Okay? So what we did, we performed another experiment. So these are the results of experiments. So this is a box plot. If you are not familiar with box plot, let me explain it for you. So since we did 10 experiments, for every theta v, there are total 3 theta v equal to 0, 0.06, 0.12. ठीक है, और हर थीटा v के लिए हमने कितने एक्सपेरिमेंट किए? 10. So these 10 experiments हमने क्या मेजर किया? Return loss. All of these 10 values are plotted here. Instead of plotting one average value, box plot plots all of these 10 values. So what does it show? It shows you, for example, here you see max of these values, this black thing, min of these values, this black thing, and then median of these values, this red thing. And then where does most of the values lie? ठीक है, उसके अराउंड ये क्या करेगा? एक ब्लू सर्कल आपको दे देगा around ±1 sigma. ठीक है, so in this way we can actually see कि this gives us much more information than the averaging. एवरेजिंग आप इन सारी 10 की 10 को एक क्वांटिटी में ले आते हैं, वो आप यहाँ पे प्लॉट कर देंगे, यहाँ पे डिपेंडिंग ऑन किसकी एवरेज क्या है. बट इन बॉक्स प्लॉट यू एक्चुअली हैव ऑल द 10 वैल्यूज इंटैक्ट. सो these are the results of experiments, but when we did Top's prediction, we get this equation for these new experiments. So how do we do calibration? So we take this dry soil as our reference. So we compute this offset of this min, जो कि आपके बॉक्स प्लॉट की जो मिनिमम वैल्यू है वहां से हम यहाँ तक एक जो है ऑफसेट कंप्यूट करते हैं, एंड देन वी सब्ट्रैक्ट इट फ्रॉम एवरीवन, फ्रॉम एवरी रीडिंग, क्योंकि वो कांस्टेंट रहता है. इफ वी डू दैट वी गेट दिस कर्व. ठीक है, सो दिस टेल्स अस कि आपके पास जो एक्सपेरिमेंटल ऑब्जर्वेशन है विच इज इन द फॉर्म ऑफ बॉक्स प्लॉट, और जो theoretical prediction है which is in the form of this blue curve, so they are in close agreement for at least this range of soil moisture. So this range is from dry soil to 12% of water content. So this is enough range for most of the applications, but we did not stop here. We actually tried to validate it in outdoor settings. So we took all of our equipment. You see here, we took laptops, our antennas, those Wi-Fi devices, everything outside in the nursery. So this rack was built by our student who was working as a senior year who was having senior year design project with us. So he took all of this equipment and performed experiment in outdoor settings. So in these four, what do you say, pieces of lands. So, but the problem in outdoor was we did not have any reference. जैसे आपको याद है हम पहले कह रहे थे कि हमारे पास थीटा वी हमें पता है क्योंकि हम जो है एक अमाउंट ऑफ सॉइल लेते हैं, फिर हम एक अमाउंट ऑफ वाटर लेते हैं, उनका वॉल्यूम मेजर करते हैं दोनों का, एंड देन वी मिक्स देम. That gives us a reference theta v. But here when you are outside, you do not know any reference. ठीक है? So for reference generation, we use those capacitive devices that you have already seen. So how did we use them? So we got a model for the readings of these capacitive devices in indoor settings like this. So in indoor settings, we varied our theta v, which we can do because we have the control over volume of soil and volume of water. And then we recorded the readings of this device, this capacitive device, the soil moisture sensor, on x-axis. We got, for example, these 7 points, these orange ones, and then we draw a fit. So you can see, you can fit them using simple a linear regression or a quadratic regression. So in this way, now we are sure that a capacitive sensor reading, for example, like a 200 आएगी, so for 200 theta v will be 0.38. अगर capacitive sensor की reading, for example, 70 आएगी, for 70 reading of this capacitive sensor, sorry, you will have theta v, which is 0.18 or 0.19, somewhere like this. So in this way, we generated our reference using these capacitive devices, but in lab settings. Now we use them here for sensing the, for generating the ground reference, for generating the reference for our experimentation. So this is the result that we obtained. Here we compare the results of indoor in the lab. So this orange one is the lab setting, and this box plot is the experiment. So both are now experimental. We have removed here Top's equation because we know that we need to do calibration on dry sample. So that is performed here for sure. So now these are the results of lab experiments and outdoor experiments. So you see they, since in outdoor we do not have control over theta v, so that is why we have some sparse readings. But in lab, since we have control over theta v, you can see all of the readings from this range from 0.15 to 0.25 of volumetric water content. So in this way, by performing a simple calibration on a dry soil sample, we were able to use the existing Wi-Fi signals for sensing something which was already being done either through invasive sensors or using satellites and so on. Now, you will be wondering what could be its application, how we can use it. So just for your reference, for example, you can take a drone and you can just put a Wi-Fi receiver and transmitter if we are able to miniaturize all of this. So on that drone, and then simply run it over the field, it is going to give you much more accurate readings with very low cost system using this setup that we have demonstrated here. Since it was an experiment, so we did not focus on miniaturizing everything. So we have to use those white boxes and those green antennas and everything. So that is it from my side. So if you have any questions, I am here to answer. So let's hear from you guys.